Hi, Chris Good here with t-test problem number 4. So if you were in the group that got this question, it's the one about the impact of REM sleep deprivation on a computerized assembly line task. So participants do 2 nights. On the nights they measure EEG, that's electroencephalography, EMG, that's electromyography, and EOG, electrooculography, which measures eye movements. They do that while they're sleeping. So on each night you get 4 hours of sleep. On one of the nights, subjects are awakened immediately upon achieving REM sleep. This is the time of the evening when people are most likely to report dreaming. On the alternate night, subjects are randomly awakened at various times throughout the 4 total sleep sessions. So they're either getting their REM sleep disturbed selectively, or their sleep disturbed randomly. So that's kind of an interesting control. This way, what's being manipulated is disruption of REM sleep in particular, which we think might be necessary for optimum performance on this task. The testing conditions are counterbalanced. That's good. Half the subjects get REM deprivation on the first night, half get it on the second night. And then they do this task, and the task is 5 rows of widgets, and randomly placed in a 1:5 ratio are widgets missing a component, and they have to be identified or fixed by the subject, and we record the number of missing widgets. Alright, how many widgets did you miss? Compute the appropriate t-test for the data provided below. Alright, let's first do our null hypothesis. This is a repeated measures design because it's the same people who are either having their REM sleep deprived or their sleep otherwise deprived. So we need to talk about the difference scores. We're going to make a null hypothesis about the population mean difference score, which we hypothesize to be 0. Okay. Step 2 is that we need to state our alpha, which I've said for all these problems is going to be 0.05, and then determine our critical value for t, and to do that we need the degrees of freedom. Well, the degrees of freedom are relative not to the number of total scores that we have, but to the number of difference scores. I'm going to go ahead and take this time to calculate the difference scores. So 26 minus 20 is 6, 15 minus 4 is 11, 8 minus 9 is negative 1, 44 minus 36 is 8, 26 minus 20 is 6, 13 minus 3 is 10, 38 minus 25 is 13, 24 minus 10 is 14, 17 minus 6 is 11, 29 minus 14 is 15, and so we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 different scores. The degrees of freedom is the number of different scores minus 1, or 10 minus 1, or 9. And the critical value for t, for 9 degrees of freedom, if we look in our handy t-table, 9 degrees of freedom at two-tailed test, alpha of 0.05 is 2.262. Plus or minus 2.262 because it is a two-tailed test. Let's go ahead and draw that curve for t, shade in that critical region. 2.262 minus 2.262. As always, the mean, mode, and median of the t distribution is 0. Do a little bit of shading there. It's supposed to be symmetrical. Try to make that curve all symmetrical there. Okay. Step number 3 is to calculate your test statistic. In this case, the repeated measures t is the mean difference score, which we haven't calculated yet, minus our hypothetical population mean difference score, divided by the estimated standard error of the mean difference score. Well, let's go ahead and calculate the mean difference score. To do that, we're going to add up all of the differences, right? I'll do it up here. The mean difference score is the sum of the different scores divided by the number of the different scores. So I've got my calculator. I'm going to do 6 plus 11 minus 1 plus 8 plus 6 plus 10, 13, 14, 11, and 15. I get 93, right? So 93, and that's divided by 10 different scores, so 9.3 is our mean difference score. All right, that's going to be handy later on. To calculate, so we've got this part. We've got this from the null hypothesis. We need the estimated standard error of the difference between, the mean difference score. Sorry. So that's the square root of the variance of the different scores over the number of different scores. What's the variance? The variance of the different scores is equal to it's the same variance as everything. Sum of squares of the different scores over degrees of freedom. How do we do sums of squares? Well, we're going to follow the computational formula, which is the sum of the squared different scores minus the square of the sum of the different scores divided by the number of the different scores. So I'm going to do these. I'm just going to look at what the squares of the different scores are, and then I'll sum them up using the calculator. 6 squared is 36, 11 squared is 121, that's 1, 64, 36, 100, 13 squared is 169, 14 squared is 196, another 121, and 15 squared I know is 225. Let's go ahead and add all these up, do our sums. 36, 121, 164, 36, 100, 169, 196, 121, and 225 sums to 1069. Right? We'll plug that in here. The sum of the different scores I got over here, 93, right? So 93 squared over 10 is going to be the second term. The square of 93 is 8649, so that's 1069 minus 8649 over 10. Of course, that just moves the decimal over. Then it's 1069 minus 864.9, or 204.1. That's our sum of squares. We'll plug it in up here. 204.1 over the degrees of freedom, which are 9, is 22.68 with rounding. I'll plug our number here for variance into the estimated standard error formula. That's 22.68 with rounding divided by the number of different scores we have, which is 10, and I end up with the square root of 2.27. That's again with rounding. Square root of which is 1.51. We'll plug this into our t equation, right? And again, this is with rounding. You might get a slightly different answer if you rounded earlier or later than I did. But I end up with 9.3 minus the value here we get from a null, which is 0. 9.3 minus 0 divided by 1.51 is 6.16. Again, that's with rounding. 6.16. If you rounded earlier or later, you might come up with 6.17 or a little bit more than that, but this is, it's all pretty close. 6.16, we're going to see where that is in the curve. Of course, it is beyond your uppermost critical value. And so the decision that we're going to make, and I'll write it down here, is to reject that null hypothesis that the treatment does nothing. Well, let's go back to the question and find out what that does mean. These differences are positive, and we got them by subtracting the control from the treatment where REM sleep is deprived. So it means that they've got a bigger number when they're REM sleep deprived. When they don't get that dream sleep, they have more, what? More widgets? No. It's the number of missing widgets that's recorded. It's the number of mistakes that they make. So we need to write our conclusion in the right direction, okay, and make sure that we interpret this correctly. So here we can say that REM sleep deprivation significantly increases The what? Well, the number of widgets they miss. I'm going to put it in terms of errors that the subject makes. So increases the number of errors made in an assembly line task compared to compared to random sleep deprivation. I'm not done with the sentence. I want to put in my statistic in the proper APA style, so I'm going to say T with 9 degrees of freedom is equal to 6.16. And the p-value, we don't know what the p-value that's associated with this, right, and beyond. But we do know that the p-value is less than the proportion under the curve bounded by our critical values. So we can say that p is less than that proportion, 0.05, and be done. And that's my answer to number 4.